Students, sorry. Now, okay. Can you hear me now? Right. Students, good morning. In last class, we studied Maxwell Boltzman distribution curves. And according to that concept, it is a particularly how velocities of gas molecules distributed among those gas molecules at particular temperature. We can observe when temperature at particular temperature, more fraction of molecules having velocity is called most probable velocity, and very few fraction of molecules are having either high velocity and low velocity. Okay, when temperature increases, the flat become, I mean, the curve becomes very flat compared to previous case, and high velocity possessing molecules increases when temperature increases. So we already studied in a last class, and this is the notes for Maxwell Boltzmann distribution curve. All the gas molecules move randomly in all directions, and they collide with other molecules or walls of the container. So they do not have constant velocities and similar velocities. Next point. Maxwell and Boltzmann studied or given distribution of velocities of gas molecules with help of theory of probability. They plotted a graph between fraction of molecules versus their velocities. Students completed. Remaining students. Okay. Here number of molecules, or you can take fraction of molecules. Both are same. Velocity. The observed graph is it is T1 temperature. And this point is most probable velocity. The next point, obviously, average velocity. The next point, obviously, most RMS velocity, because RMS velocity always greater than average velocity. Average velocity always greater than most probable velocity. See, if they touch x-axis, then fraction of molecules become zero. So they never touch. They never touch. When this curve touches with this axis, x-axis, then fraction of molecules zero at that particular velocity. So it never occur. So students here, after peak, this peak is represents most probable velocity next to average velocity next to RMS velocity. Okay. When it is temperature T1, when temperature rises, same number of molecules are present, but the flat will be like this. So it is at temperature T2. Students completed? Okay. Results from these graphs. First result, low fraction of molecules possessing very high velocity and very low velocity. So low fraction of molecules possessing very high and very low velocity. Second point, fraction of molecules possessing or possesses higher and higher velocities goes on increasing till it reaches a peak. Thereafter it start decreasing. Fraction of molecule possesses higher and higher velocities goes on increasing till it reaches a peak. Thereafter it start decreasing. Next, maximum fraction of molecules possessing velocity is called most probable velocity. So these are the results from distribution curve.
Sir, 1 minute, sir. Simhadri, sir. Good morning.
Good morning, sir.
Students, log in with your name only. Don't log in with other names, with your father names, and mention your section. All of you mention your section. And yesterday, so many students are absent. In 8 to 9 also, CASR class also, 7 members absent. 12 to 1, 6 members absent. And 2 to 3 p.m. Physics, PSGSR class, totally 13 members absent. So I want to say one thing. I will take attendance and inform to your parents only. It is genuine problem. It's okay. We will accept. Otherwise, we don't accept. And everybody write with your name and section also. You have to mention your section. That is very important. So some students are coming in one class and some students are coming not attending the another class. We don't accept. If you genuine reason, you have to inform me. Otherwise, we don't allow the classes without information. This is not not a shopping mall. Whenever you're interested, you have to come to and go to outside. So I will take attendance. Those who are not attending, I will inform to your parents immediately. And one more thing, don't send that details. I told so many times. I raised group also. Some students are not up to now not send that details and JPG format of photo also. So immediately that will also complete today only. Do you have any doubts? Call me. Sir, thank you, sir.
Okay, sir. Right. The students completed. Okay. So next, temperature effect. When temperature rises, when temperature rises, then velocities of gas molecules changed in different way. We observed already. So temperature effect, first point, when temperature increases, when temperature increases, what we observed, the curve shifted to right side. The curve shifted to right side. And one more point you can observe, initially at temperature T1, it is very narrow. When temperature rises, the curve even more flatter than previous temperature. It is T2. Next point. The fraction of molecules possessing high velocity, the fraction of molecules possessing high velocity are increased, and the fraction of molecule possessing low velocity are decreased. And third point is the fraction of molecules possessing most probable velocity also increased. In temperature T1, we can observe it's a narrow curve and we can see exactly at the peak of the curve. Under peak of the curve, how many number of molecules are present? Those are having most probable velocity. I think that fraction of molecules very low. When temperature increases, the curve even more broad compared to previous case. Then we can't see exactly the peak of the curve, but because it's more flatter than previous case. So under this curve, we can see more number of molecules. That's why the fraction of molecule possessing most probable velocity also increased. So this is about temperature effect. Completed. Yes. Next, mass effect. Molecular molecular weight effect. Let us consider two gases, A gas and B gas. Molecular weight of A gas in case greater than molecular weight of B gas. Then if you draw probability distribution curves for two gas at same temperature, fraction of molecules and velocities. Ma more mass, Mb very low mass. Low mass containing gas molecule velocity is definitely very low, because mass of the gas increases, it is very difficult to move. Okay, in normal example also we can understand heavy person cannot move, 110 kg person and 55 kg person. So who can very easily run? Definitely 55 kg person. Similarly, which are having high mass, the velocity is also very low. Okay, so this graph related to Ma. And what about Mb? Let us consider same molecules here, 100 molecules, here 100 molecules. This is for Mb, somewhat higher than A molecules, because mass is very low. The velocity also very high compared to A gas molecules. So in case if you get question on three different masses of gases, then you can expect this kind of graph. So student, this is about Maxwell Boltzman distribution curves. Yes, completed students. Okay. And the next concept is deviation of or deviation from ideal behavior. So this topic related to real gases. Ideal gas, real gas. Ideal gas, we already studied, the gas which obeys all gas laws at any temperature, at any pressure, or the gas which obeys ideal gas equation is called ideal gas. And what is real gas? Very simple. Which do not obey ideal gas equation is called real gas. PV equal to nRT, that is ideal gas. PV not equal to nRT, that is real gas. Yes, you can understand which gas is real gas, which gas is ideal gas. According to Boyle's law, at constant temperature, pressure is inversely proportional to volume. Even we drawn many graphs P versus V at constant temperature. We call them as a isotherms. Students, Van Revel, scientist Van Revel, he studied some gases, most of the gases, whether the gases obeys PV equal to nRT at all conditions or not. Okay, so he tried to understand whether ideal gas equation is correct for each and every gas at all temperature and all pressures, or at what condition gases obey ideal gas equation, at what condition gases do not obey ideal gas equation. It is completely experimental result. Okay, he took carbon dioxide or nitrogen because many gases are there. Let us consider nitrogen gas. According to PV equal to nRT equation at constant temperature, temperature is constant, R is constant, fixed amount of gas. So nRT value is constant, PV equal to constant. Then we can easily apply different pressures and different volumes. According to equation, if I take pressure 2, what is the volume? If I take pressure 3, what is the volume? We can easily measure by P1 by P1 V1 equal to P2 V2. So by using this formula, this is the obtained graph. And experimentally, the experimental graph is so this is the experimental graph. This blue line is experimental. This black line is theoretical line. See, curve is same, but this experimental results do not match with the ideal conditions. Some point here, at this point, maybe they are very close to each other, but this experimental value does not match with the ideal value. What is the reason? Based on this experiment, not only nitrogen, he did many, he did on many gases. And one more point he observed, all gases, nitrogen, carbon dioxide, sulfur dioxide, oxygen, hydrogen, according to Charles' law, the minimum temperature of any gas is 273.15 degrees Celsius at 0 Kelvin. We know that we already studied at 0 Kelvin, no gas is available. So any ideal gas may be liquefied at minus 273.15. Then what about minus 273.15? And what about minus 200? You can see the presence of gas. Okay, but nitrogen is the gas having very lowest boiling point, and that is minus 196 degrees Celsius. So the experimental observed value for all gases, in that nitrogen has least boiling point minus 196 degrees Celsius. But Charles is saying the least boiling point of gas is minus 273.15. So these results are actually not matched with Charlie's experiments. So based on many results, Van der Waal said there is no ideal gas. There is no ideal gas. Ideal gas is a hypothetical gas. No gas obeys ideal gas condition at all temperature and all pressure. Maybe somewhere the gas may be matched with ideal gas, but he said at all conditions, at any pressure, at any temperature, no gas obeys ideal gas equation, and that is called real gas. So he said in atmosphere the gas is available, all are real gases, all are real gases, no gas is ideal. And in a general observation, can you say this person is ideal? Can you say this one is ideal? Definitely you cannot say, because let us fix for teacher. I'm a teacher. What is the qualities of teacher? I'm an ideal teacher? Definitely not, because there are certain parameters for the ideal teacher. Maybe 100 qualities, maybe 10 qualities, but no one teacher satisfy all qualities, because they have some demerits. According to protocol, they have given certain parameters for a good teacher, but no one uh, agree. I mean, no one follows that. Maybe they follow 99 percentage or 99.99 percentage, but never 100. So no one is ideal. Similarly, no gas is ideal. It is a hypothetical. Are you getting my point? Can you say he's a good politician? No, definitely not. Can you say he's a good, very good businessman? Ideal businessman? No. Even in 1 lakh, you can't see who obeys all the qualities. It is very difficult. So always ideal is unique. Ideal is unique. Okay. So same thing we can apply for gases also. No gas is ideal. All are real gases, but they can also obey ideal conditions at particular temperature and particular pressure. See, the graph is very close to ideal behavior at particular pressure. Maybe at this condition, the real gas behaves as an ideal gas. Are you getting my point, students? What I'm trying to say, Boyles, Charles, and Gay Lussac, they did very good experiments, no doubt. But those conditions are applicable to particular values. I mean, pressure is inversely proportional to volume. Yes. But if you apply for particular gas according to ideal condition is different from real condition. See this point. At certain, this pressure is, in case pressure is constant, if you observe volume of ideal and volume of actually observed, theoretically at this pressure, this is the value, but experimentally the value is more. So ideal gas is a hypothetical gas. Students, are you understand? Are you getting my point? Hello, students, can you hear me? Yes. Do you understand my point? Do you understand my point? My point is gases are obeys ideal gas, but at particular conditions only, not in all conditions. Conditions apply. Yes, that is the point. So even also we can also apply for certain reimbursement, but in all conditions we won't get. We should follow terms and conditions. Similarly, a gas also should should qualify for the particular conditions. Okay. In tomorrow class, students, you can understand in a I mean you can understand because we are going to study one more graph, then you can understand. Okay, thank you, students. Yes,